The issue we'll talk about now is the stability of cycloalkane. As I mentioned in the introduction to cycloalkanes, formally these molecules can be constructed by taking a linear alkane and then twisting its ends until we reach a circular structure. And this process cannot be equally facile for a large alkane, which can be twisted very readily, or for a small alkane, where a lot of twisting is required to be spread out over a very small number of atoms. And the first person to realize that was Adolf von Baeyer, who actually got a Nobel Prize for his work in 1905. And who introduced the concept of the ring strain, which comes from the fact that carbons want to be tetrahedral, but they're not in circular compounds, because simply a certain circle can accommodate only this certain angles. And so ring strain really comes from distortion from tetrahedral angle of 109.5 degrees in cyclic compounds. If you look at the structures of small rings, cyclopropane has an internal angle of 60 degrees, cyclobutane has a corresponding angle of 90 degrees, cyclopentane is 108, so it's actually pretty close to the 109, and then cyclohexane is 120, and so forth. And clearly in cyclopropane this distortion is the largest, it's about 49 degrees, and it's slightly smaller in cyclobutane. Another problem is the torsional strain. If we look at the cyclobutane and approximate it as a planar structure, and then look down these two parallel bonds, what we'll see is basically a relationship where all interactions are eclipsing between hydrogens as well as between the CC bonds. And so that introduces a lot of instability in these systems as well. So this is fully eclipsed. Well, the question is, how do we measure these instabilities, and how do we measure the stability of a compound? And it might come as a bit of a shock to you that to measure the stability of a compound, the thing that chemists do is burn it. So if this is a cycloalkane of certain general formula, we can react it with 3 half ends of oxygen from air to give us n moles of CO2 and n moles of H2O and a certain amount of energy. And the more carbon atoms we have, the more energy we'll get. So cyclohexane is almost twice as energetic in this combustion process than cyclopropane. So this energy, in order to be able to compare different alkanes and cycloalkanes, is typically expressed per CH2 group. In other words, we take the total amount of energy and we divide it by the number of CH2 groups, number of carbon atoms in a ring, and then we get this energy of combustion per CH2. Now, how does this work? Well, if we have a certain stable compound and we burn this compound, then we'll get 2 more stable compounds. We'll get CO2 plus H2O, and they're very stable. And so we're going energetically downhill, and this is our energy of combustion, which is being released. If we have an unstable compound, the compound will be higher in energy. But it will still, provided they're isomers, it will still be composed to same CO2 and H2O, which are very stable. And this difference in stability, this difference in energy between stable and unstable compounds represents strain or other sources of instability. Let's see how that works out for now. Before we get into cycloalkanes, the stable compound in this case has to be some sort of a reference compound. A stable compound is defined as a long chain alkane, long chain linear alkane, which is typically chosen to be very long so that the effects of the terminal CH3 groups are relatively negligible, and since obviously it's linear, it's not significantly straight. And for this reference compound, the delta E, the E combustion, equals per CH2 group equals 157 kilocalories per mole. Let's see how these, what numbers do we get for other cycloalkanes? Cyclopropane, cyclopentane, and hexane. We get these delta E values of CH2 of 166. All these numbers are in kilocalories per mole. 163, 158.7, and 157. Okay. Now, if we subtract the combustion energy of the stable compound, we'll basically get this ring strain in these compounds, and this difference will be the largest in the case of cyclopropane, about 9 kilocalories per mole, and 6, and 1.7, and 0. Okay? Which tells us that cyclopropane, as expected, is the most strained compound. And this, indeed, this problem with strain comes from the difference of this angle, which is supposed to be 60 degrees, and the tetrahedral angle, which is 109 degrees. In the next topic, we'll go into the structures of a couple of small alkanes, small cycloalkanes, before we finish this lecture today with the pretty detailed discussion of cyclohexanes.